This video lecture is about the Jovian planets and their rings. Jovian means Jupiter-like. So Jovian planets are gas liquid worlds like Jupiter with much smaller densities than those for the terrestrial planets. The ones in our solar system have densities from 0.7 for Saturn on up to 1.6 for Neptune. They're made of mostly hydrogen, helium, and hydrogen compounds and have thick atmospheres. Compared to the other Jovian planets in our galaxy, Jupiter is not the most massive planet, but it is about as large in diameter as a planet can get. Adding any more material to Jupiter would make it smaller in diameter because of the increased gravitational compression. The Jovian planets spin rapidly, which is why they are noticeably oblate, which means they are flattened at the poles and bulge at the equator. Jupiter spins the fastest at 9.925 hours, while Uranus spins the slowest at 17.24 hours. Saturn is the most oblate, and Neptune the least. One can use the oblateness to tell us about what the interior is like. Next slide. The techniques we use for probing a Jovian planet's interior are almost the same as what we use for the terrestrial planets, though we can't have landers and do seismology, of course, because there's no surface to land on. Only Jupiter has had a probe go into it to take data directly from the atmosphere in situ. The Galileo probe got down to 22 bars, that's 22 atmospheres worth, or 161 kilometers below the cloud tops, where the temperature reached 426 Kelvin. That's 307 degrees Fahrenheit. That depth is still just 0.3% of Jupiter's radius. As a reference, the pressure felt by a submarine at the bottom of the Marianas Trench on Earth is 1,100 bar. The list of tools includes laboratory experiments of how hydrogen and helium behave under immense pressure and temperature, and then we extrapolate based on our knowledge of quantum mechanics to predict what Jupiter and Saturn have enough gravitational compression to turn some of their hydrogen into strange stuff called liquid metallic hydrogen, where the atoms are squeezed so much that the electrons are pushed out of the atoms to roam freely in the liquid hydrogen. The metal property is that they are able to conduct electricity and produce a magnetic field. We put the data together into computer models of each layer of the planet, and layer by layer we build up a picture of the interior structure. Notice how temperature and pressure increase going towards the core, and also that the Jovian planets are mostly liquid. The Jovian planets have a lot of internal heat. In fact, Jupiter, Saturn, and Neptune radiate more heat energy than they receive from the Sun. A terrestrial planet's surface and atmosphere temperature is due to the Sun, solar heating. The Jovian planet's atmosphere temperature is from internal heat and from the Sun. There are two sources of the internal heat. One, leftover heat from their formation, which makes up the great majority of their internal heat. And the second is contraction in the case of Jupiter and Neptune, and differentiation in the case of Saturn. Contracting gas will heat up from the conversion of gravitational potential energy to thermal energy. The Jovian planets are mostly liquid, so the contraction is small and gradual. Saturn is not contracting, but the helium is able to separate from the hydrogen and sink to the core, releasing gravitational potential energy, heat. Next slide. The Jovian planets have the standard atmosphere layers. Thermosphere at the top, heated by X-ray heating. Stratosphere from the absorption of the ultraviolet light from the sun, and the haze layer is in there. And the troposphere, where convection and clouds are found. These pictures from the Galileo orbiter show Jupiter's appearance as viewed at various near-infrared wavelengths, with distinct differences due primarily to variations in the altitudes and opacities, that is, how transparent they are, of the cloud systems. Therefore, some wavelengths are from deeper regions, and some just from the top-level haze. Note that the Great Red Spot is a high-pressure storm above the rest of the clouds. Whereas the terrestrials have basically one layer of clouds, the Jovian planets have distinct layers of clouds. Jupiter and Saturn have 3 layers of clouds that we can see. All of the Jovian planets have ammonia, ammonium hydrosulfide, water, and methane gas all throughout their atmosphere. These gases condense or freeze at different temperatures. Different heights in a given atmosphere are at different temperatures. Jupiter's greater gravity compression and warmer temperatures mean its cloud decks are a bit closer together and higher up than Saturn's. Uranus and Neptune are so cold that the ammonia and ammonium hydrosulfide and water clouds would be too deep to see. Uranus and Neptune are so cold that methane clouds can form. There are no methane clouds in Jupiter and Saturn. Next slide. Jupiter's clouds are the most colorful and distinctive. In the bands, we see opposite motions of adjacent bands moving at hundreds of miles per hour. The graphic shows a schematic of the zones and belts. The high white ammonia clouds are above the red-brown ammonium hydrosulfide clouds. Rising ammonia clouds have ammonia snow, so descending air lacks ammonia. Occasional blue patches are visible among clouds, and they are places where the clouds have cleared to see the deeper layer underneath the cloud deck. Next slide. Jupiter's Great Red Spot is a high-pressure hurricane that has been going on for hundreds of years. It is larger than the Earth. Jupiter has no mountains or solid surface to disrupt storms, so they can last a long time. Same thing goes for the other Jovian planets. Check out the Saturn cyclone video. Neptune's Great Dark Spot, first seen by the Voyager spacecraft during its flyby in 1989, was the size of the Earth. However, it disappeared a few years later, so even the big storms don't last forever. Next slide. Now we'll take a look at something that extends far beyond the atmosphere, but is generated deep in the interior, the magnetic field. The region of space around the planet in which the magnetic field is found is called the magnetosphere. We think that Jupiter and Saturn's magnetic fields are produced in their liquid metallic hydrogen layer, though measurements of Jupiter's magnetic field by the Juno spacecraft seem to show that at least part of the Jupiter's magnetic field is generated higher up than that layer. Jupiter's magnetic field is enormous. Note that the picture shows the Earth's magnetosphere has been enlarged 10 times to compare it to Jupiter's, and even then it is still dwarfed. Jupiter has a lot more metallic hydrogen than Saturn, and Jupiter spins faster than Saturn. Jupiter's magnetospheric extent is so great that it would be about 4 times the size of the Moon as seen from the Earth. Jupiter's magnetic field also has more charged particles than the other Jovian planets because of Io. Jupiter's magnetosphere deflects the solar wind at a great distance, but the charged particles trapped in its inner magnetic field are from gases escaping from Io's volcanoes to create a ring of charged particles encircling Jupiter. Any spacecraft we send in close to Jupiter has to be specially radiation hardened to protect the electronics, and even then they still decay and fail after a few years. There is a 3 million amp flux tube connecting Io and Jupiter. Any human getting in close to Jupiter would be killed instantly from the intense radiation. Uranus and Neptune don't have enough internal pressure to liquefy the hydrogen, much less even to turn it metallic. Their magnetic fields may be generated from a solution of ammonia and water that creates freely moving ions in the water-ammonia mantle. But why are they offset and greatly tilted? Clearly, we still have a lot to learn about how magnetic fields are generated.